Hi everyone, my name is Travis, and today I'll be telling you about joint work with my collaborators at the University of Pennsylvania on fair consumer finance. The high-level goal for this project is to think about ways to design a small number of investment portfolios that will fairly serve a large population of investors or consumers. And so there's a lot to unpack there, but I want to start by being a bit more precise about what we mean by fairness in this setting. So we suppose that the population is divided into subgroups, and at least at a very rough level, our goal is to ensure that all of these subgroups are happy with the portfolios that we've designed. So to give a simplified example, consider a university that offers retirement savings plans to its employees, where under the hood, each of these plans is an investment portfolio that the employees can choose to invest in. So for this setting, the groups that we're trying to treat fairly might be the different employee types at the university, right? So for example, there are faculty, graduate students, administrative staff, and so on. And we want to make sure that all of these different employee types are happy with the plans being offered by the university. Okay, so since we're interested in designing investment portfolios, I want to quickly make sure that we're on the same page about what those are. So an investment portfolio is a mixture of financial assets, and typically portfolios will have higher returns and lower risk than investing in an individual asset alone. And here we're thinking about the risk of a portfolio in terms of the variance of the returns that it provides. And of course, there's a trade-off between how risky a portfolio is and how high its return can be. And this leads to a risk-return frontier that says for any given risk threshold, what is the optimum return that you can get for a portfolio designed over a set of assets with risk not exceeding that threshold. So for example, for this specific risk threshold C, we can optimize the portfolio to maximize return, which gives us the allocation shown on the right. This is optimized over the assets that we use in our experiments in this work. But the thing I want to point out here is that since we can always use this standard machinery to recover a portfolio from a risk threshold, in the rest of the talk, we're going to be defining portfolios just implicitly in terms of their risk thresholds. Okay, so the reason we care about this risk-return frontier in the first place is that consumers themselves are risk-averse. So each consumer in our population has a risk tolerance, and they're unwilling to invest in any portfolio that has higher risk than that. So the input to our portfolio design problem is going to be a collection of n consumer risk thresholds, and our goal is to output p portfolios, each defined by a risk value. So we're outputting p numbers that are defining the risks of these p different portfolios that we're offering. I haven't said how we're optimizing those portfolios yet, but once we've committed to a set of portfolios, each consumer will choose to invest in the highest return portfolio that does not exceed their risk tolerance. So pictorially, I've plotted some consumer risk thresholds using blue squares and 3 portfolios of different risk values with green circles. And under this model, the first 3 consumers get assigned to that first portfolio, the next 4 get assigned to the second portfolio, and the remaining consumers get assigned to the third portfolio. And of course, when we do this, each consumer suffers from some regret, which is the amount of return that they've left on the table by using one of the portfolios we offered compared to one that was designed specifically for their risk threshold. And in the rest of the talk, we're going to be looking at the regrets of different subgroups. So we use the notation R sub A of C to denote the average regret for consumers in the set A when offered portfolios given by this vector C of risk values. Okay, so far we've talked about the inputs and outputs to the portfolio design problem, but we haven't said anything about what we should be trying to optimize for. And so the first main contribution of our work is to propose a fairness-motivated objective for this problem. So the high-level idea is that we propose to optimize a quantity called the minimax group regret, which is the average regret of the most regretful group for a set of portfolios. So the way to think about this is that a collection of portfolios will only have low minimax group regret if every group's regret is low. So even if some portfolios do a good job of serving all but one group, if that remaining group is unhappy, we will deem that those portfolios are not doing well according to our objective. And of course, this leads to fairness in the design portfolios because the designer cannot prioritize any one group over the rest unless they happen to be the highest regret group. Okay, so I think to help understand and motivate this definition, it's helpful to compare it against some other objectives that you might use for the same problem. And so the first objective to compare against is the most natural non-fairness oriented objective, which is to minimize the average regret of the entire population, ignoring the group structure. So this is equivalent to maximizing the total return for the population. So it's like maximizing the value you're generating. But unfortunately, optimizing this objective can lead to unfair portfolios in many different subtle ways. But just to give one concrete example of what could go wrong, minority groups will have a small influence on the average regret of the entire population. And so a designer that's optimizing the average regret for the whole population can essentially ignore these minority groups, which is maybe not what we want. So the second objective that I think it's worth comparing against is minimizing that average regret for the entire population, but subject to the constraint that any pair of groups has the same or nearly the same regret. But there's sort of two reasons that we don't use this objective. The first one is that it turns out that it's actually a little bit ill-defined. So for many populations, it's impossible to actually achieve equal regret among the groups. And so just to give one extreme example, imagine that one group in the population has only consumers with zero risk tolerance. So those consumers will always keep their money as cash and not use any of the portfolios that we designed. And that's what they want, so they have zero regret. And then in that case, unless it's possible for every other group to achieve zero regret using just P portfolios, this problem would be infeasible. The second and maybe more compelling reason not to use this objective is that it's Pareto dominated by the minimax group regret solution. And all I mean by that is that if you look at the regret for each group, when you solve this optimization problem compared to minimizing the minimax group regret, the only thing that can happen is that the regret for each group will be lower or the same in the minimax group regret solution. So everyone benefits from switching to that objective. Okay, so now that we have the fair portfolio design problem defined, I'm going to switch gears a little bit and talk about how to actually solve that problem. And in the paper, we provide 4 different algorithms that differ mostly in the amount of structure they require from the underlying population subgroups, and conversely, in the strength of the guarantee that they're able to provide. So there's this sort of spectrum of like less structured subgroups to more structured subgroups. And on the sort of the most general algorithm that we provide is a randomized algorithm that makes no assumption at all on the underlying subgroup structure. It's always efficient, and it outputs a distribution over sets of P portfolios that minimizes a version of the minimax group regret that's sort of tailored for distributions over solutions. However, in most applications, a distribution over solutions is not super useful on its own. And so what we really like is a concrete set of P portfolios that we can use to actually offer to our population of investors. And so we also provide a heuristic for converting the distribution that gets output by this randomized algorithm into a good set of exactly P portfolios. We don't really have very many theoretical guarantees for this heuristic, but empirically we find that it performs very well. Our next algorithm is a dynamic programming algorithm that optimally outputs a set of P portfolios that minimizes the maximum group regret, but it has running time that's exponential in the number of groups. So as long as we have a small number of groups, say 4 or 5, this algorithm can be used, but beyond that, it might become a little bit expensive. And then finally, we have an algorithm that works for the case when the groups form intervals in risk space. So I just mean that each group has like an interval, all of its consumers belong to that, have risk thresholds in that interval, and those intervals are disjoint. And in that case, we provide an algorithm that optimizes the minimax group regret, and it runs in polynomial time with respect to all of the problem parameters. Okay, but in the talk today, I'm just going to focus on this randomized algorithm and this pruning or sparsification heuristic. But I'm happy to talk about the other ones offline, and they're in the paper as well. Okay, so I mentioned that the randomized algorithm is going to output a distribution over sets of P portfolios, and that it optimizes sort of a distributional version of the minimax group regret. So I just want to quickly say a little bit more about that. So in this case, we're going to propose that you should optimize what we call the ex-ante minimax group regret, which is exactly the same as the deterministic version that we already defined, except now we're optimizing over distributions over portfolios rather than over sets of P portfolios themselves. And we're going to try to find a distribution that minimizes the expected regret of the group that has the highest expected regret for a set of portfolios sampled from that distribution. And so here, this distribution that we're optimizing over is over P sets of portfolios. Okay, this is a bit of a slightly weaker fairness objective than what we talked about already, because it only guarantees that the distribution pi is fair, but a realization of P portfolios sampled from that distribution might not be. Okay, and so the way we're thinking about this is that it guarantees that the algorithm itself is not systematically treating any group unfairly, but when it comes time to actually like flip the coins and generate one of these specific sets of products, some groups might get unlucky. Okay, so just to distinguish this from the previous definition, we'll call the previous one ex post minimax group regret. All right, so what can we say about our ability to optimize ex ante minimax group regret? So we provide an algorithm that, given the consumer risk thresholds and the group structure, will output a distribution over sets of P portfolios that's within epsilon of the optimal distribution and runs in time n squared P over epsilon squared. Okay, so the high-level idea behind this algorithm is to formulate this optimization problem as a two-player zero-sum game. One of the players is a portfolio designer that tries to minimize regret, while the other player is an adversary that tries to identify the highest regret group. So on each round of this game, the designer will solve a weighted version of the non-fair regret minimization problem, which I'll come back to in just a second. And the adversary will use the exponentially weighted forecaster to predict a high regret group. Okay, and then after T rounds of play between these two players, the empirical distribution of the portfolios played by the designer will be within 1 over square root T of the optimal ex ante minimax group regret. So you just play the game for enough rounds, you take this empirical distribution, and that's a pretty close approximation to the optimal distribution that you could get. Of course, to make this algorithm efficient, we need to specify a procedure that the designer can use to minimize this weighted population regret. And so we also give a dynamic programming solution for this problem that can minimize the weighted population regret in time n squared times P. And the key idea here is that this regret minimization problem looks a lot like a one-dimensional k-median clustering problem. So for example, if you imagine sort of plotting some consumer risk thresholds that have these two well-separated clusters, it sort of seems intuitive that in order to minimize their average regret, you need to choose portfolios that serve each of the groups independently. So maybe these two portfolios are the optimal solution. And so given the similarity to one-dimensional clustering problems, we can adapt the dynamic programming solutions for one-dimensional clustering to this problem. Just to give you a sense of how those recurrence relations work out, imagine that we knew the highest risk portfolio in the optimal solution. So then we know that every consumer with risk threshold greater than that portfolio will be assigned to that one. And then we're faced with a subproblem where the goal is to design P-1 regret minimizing portfolios for the remaining population. So putting this together, the two-player game together with this dynamic programming for solving the regret minimization problem leads to an efficient algorithm for optimizing ex ante minimax group regret under no assumptions about the underlying group structure. Okay, of course, we want to get deterministic algorithms that output just P portfolios and not distributions over P portfolios. And so one thing that we noticed after looking at the solutions in the output of this two-player game is that many of the portfolio sets in its support look very similar, right? So for example, imagine that we're trying to find sets of 3 portfolios. It could be that the first point or the first solution in the support of the distribution output by the algorithm contains these 3 portfolios. The next point in the support contains these 3, and a different solution contains these 3. And one idea for converting this distribution into a set of exactly P equals 3 portfolios is to try to remove redundant portfolios from this union. So for example, one thing that you might try is greedily dropping the higher risk portfolio from the pair of closest portfolios. So you might drop this portfolio first and repeatedly do that until we're left with exactly 3 portfolios left. Or alternatively, you can actually formulate a clustering problem where your goal is to find a set of P portfolios that minimizes the maximum distance that any product that's removed has to travel to reach a portfolio that was not removed. Okay, so we don't really have formal guarantees for how this sort of sparsification heuristic works, but empirically we find that both strategies work very well, and in particular the clustering approach is a little bit more performant. Okay, So the last sort of algorithmic thing I want to talk about is how do we deal with very large populations? And so there's two challenges with large populations. The first one is that it might not really be feasible to collect information about their risk tolerances, right? Like this might involve conducting a survey, having someone, go out and actually talk to these people and figure out what their risk thresholds are. And that might not be a feasible thing to do if you have like thousands or tens of thousands of consumers. And then on top of that, the running time of all the algorithms we've proposed scales quadratically with the population size. So if you start getting large populations, it could actually be kind of a formidable running time to design these portfolios. And so to handle this, we take a learning approach where first we sample a representative collection of consumers from the entire population. We design portfolios to try to minimize the mini-max group regret for that population. And then we offer those same portfolios to the entire population, even though they were designed just for the sample. And so sort of the key question for this approach is how big does that sample need to be in order to guarantee that this will perform well? And what we show is that if you draw a sample of size roughly 1 over epsilon squared times 1 over W min squared, where W min is the fraction of consumers belonging to the smallest group, then with high probability, for any set of P portfolios that you might choose, the maximum group regret on the sample is within epsilon of the maximum group regret on the entire population. And so this means that if you design portfolios for the sample, they will perform pretty much exactly the same when you use them for the entire population as well. So one interesting aspect of this bound is that the generalization sample complexity does not depend on the number of portfolios being offered. And this is a bit surprising, given that in the paper, we're also able to prove a lower bound of P on the pseudodimension of the relevant class of functions for this learning problem. So there's some nice cancellation that works out in the definition of minimax regret that allows us to sort of escape this dependence on the number of number of portfolios. Okay, so finally, I'd like to talk a bit about some experiments that we carried out, evaluating our algorithms and several baselines on real financial data from the 50 most liquid publicly traded US equities during the time span of 2005 to 2020. The consumer risk thresholds and their group structures in these experiments are synthetically generated. And what we do is for various values of P, the number of portfolios, we plot the minimax average group regret for the dynamic program that minimizes the population regret, our two-player game plus sparsification heuristic, and also for the optimal set of P portfolios obtained by solving an inefficient integer linear program. And so there's two high-level takeaways. The first one is that optimizing population regret does not lead to low minimax group regret. So we do need fairness-aware algorithms in this space. And the second one is that if you use our solution from the game plus heuristic with P plus 1 portfolios, it typically achieves lower regret than the ILP optimal solution for P portfolios. So this is evidence that these heuristics are actually performing quite well. That's all I have, so thanks very much.